Hi, in this segment we're going to talk about how we can extract certain properties from the stress strain curve in a material, and the properties will be useful later for the design. We also will discuss a few ideas about giving the material a higher level of strength that would be required in some design applications. So in principle, what we will be discussing today is the idea of torsional strength of the material and how this compares to tensile properties. And then we move on to defining from the tensile properties the concept of resilience, the concept of toughness, the hardness of the material, and also for dynamic loading, the impact properties. And later in the segment, we will discuss the statistics of strength, since the material can have a variety of strength levels depending on the surface finish and the defect content and the lot handling and the grain size and so forth. And perhaps in the next segment, after this lecture, the next lecture, we can discuss the cold work and how we make the material stronger. So let's start with torsion. So as we know that torsion is application of a torque. So if you have a rod and then you apply a torque on this rod, the rod is going to twist. So the angle at which it twists is called the twist angle. So if you look here, this is the top view. The top view is going to look like a circle like this, and the circle has a center. And then if you take a ray from the center of the circle to the outside perimeter, this is outside perimeter, then after the application of the torque, every point on this ray is going to move an angle theta. And this angle theta defines the movement from this ray to the corresponding ray here. So if you look from the top, you have a triangle that is defined by theta. The distance that we describe here is r theta. So if we look at this length of the cord, it is r theta. That's the maximum value of the length of the cord. Rho is the radius from the center to any point here. So if rho exceeds this point, it will continue up to the surface. Then on the surface, rho will be equal to r, the radius of the solid shaft. The length of the shaft is L0, as you can see here. And if I have on the outside of the shaft a fiber, for example, this fiber here, and the end point of the fiber is fixed, then after the twist, if I apply a twist here, then this fiber becomes the green fiber that was there, and the angle that describes this motion is gamma. It's called gamma. So this angle gamma is in radians is equal to the strain. So the strain is equal to the angle gamma. So you have to realize now that we have two angles. One from the top is called the twist angle theta, and one from the bottom, which is the side here, this angle here, gamma, that describes the shearing motion, and this angle is the shear strain. So if I define the stress as pure shear, tau is pure shear, is equal to the rigidity modulus, or the shear modulus, times this angle gamma that describes that shear. And that gamma is dependent on how far one is from the center. So if one is on the surface, gamma is gamma max, and it's equal to the arc length divided by L0. So this is here L0 to be specific, because you have a very long triangle here, and the triangle, you will see that looks like that. From the top is r theta. From the side, it is approximately L0, and this angle here is gamma. So gamma is approximately R theta divided by L0. That's the gamma max. Therefore, if for R equals rho max, we will be able to define the shear stress on the material. Also, so if I go back, the shear stress will be G times gamma, and gamma max, or G times gamma max, and gamma max is R theta over L0. So the tau max will be equal to G times gamma max, which is R theta divided by L0. So this is from the strain, gamma, and this is the shear modulus. We'll multiply them together. If we apply equilibrium, however, we can also find that tau max is equal to the applied torque times R over J, where J is called the polar moment of inertia, and that is equal to 1/2 pi R to the power 4. So both approaches, this is using kinematics, and the top one is using equilibrium. They should be the same, give me the same value of the maximum applied shear. Now the question is, if I take a bar and I torque it initially and let go, then it will go back to the original location or the original shape. If I exceed a certain point, then the bar will go into plastic deformation, and if I let go, then it will just go a little bit, not entire range. Very, very similar to the case of tension tests. So let's look at the test that is performed. So if you look at here, this is if you plot tau versus theta, the twist angle. Tau is going to increase linearly with theta, and then it will start having nonlinear behavior because of plastic deformation, and then it will continue on up to the failure point we can call it F in here. So there's going to be a point that describes the yield. This is the elastic limit, and this is the yield point. So the yield point, we're going to call it S shear yield. So this is the yield strength in shear as described in here, that level of the tau that makes the material yield and shear, which is approximately about 1/2 of the yield strength in tension. Correspondingly, we can also find another property that describes the ultimate strength in torsion, and that will be S shear ultimate. And with these two, we can completely describe the torsion test. Let's now move on to discuss resilience and toughness. If you say that someone is resilient, it means that this person can take a lot of forces. Once the forces are removed, then the person kind of bounces back completely, if you will. However, if you describe someone as tough, that person can take a lot of forces, again, usually higher levels of forces, and he bounces back with some broken bones and some kind of, blemishes on his face, and therefore we can call him tough. That's the same idea for materials. There is the resilience describes elasticity, and the toughness describes the entire energy that can be absorbed in before failure. So if you plot the stress strain curve in here, so this is the stress sigma, this is the strain, then you can define a proportional limit, an elastic limit, a yield point. These are the 3 points that are almost indistinguishable in many cases. The area under the curve is the resilience, which is the energy absorbed per unit volume. So I'm going to say that energy per unit volume is, in this case, in joules per meter cube, for example, is the modulus of resilience. And therefore I can calculate the modulus of resilience as the integral from 0 to epsilon yield sigma d epsilon, which is approximately equal to the area of the triangle, 1/2 the yield strength times the yield strain. And if we ignore the differences between the location of these 3 points, that the yield is essentially the same as the proportional limit, you can make this approximation as 1/2 is the times the yield strength squared over E. Same idea, we can apply it for toughness, and toughness is defined here as the capacity of the material to absorb energy without fracture. That's the toughness, which is again the area under the sigma epsilon curve up to fracture. So we can define U sub t, which is the units of that is joules per meter cube, as the integral from 0 to epsilon fracture f of sigma d epsilon. And here we don't want to do anything sophisticated like a numerical integration. So we take the average value of the yield strength and the ultimate strength and multiply that by the fracture strain, which is like approximately the area of a rectangle that represents the entire curve. And if I'm using the British standard units, it will be pound force inch per inch cube. That defines the toughness. Let's now discuss what happens if I have a lot from which I chose a sample randomly, and I went to the lab and then I put it to testing in a machine, and I tested the stress strain curve, and from that I found the ultimate strength of the material. Obviously depending on the surface finish, the grain size, the cooling parameters, the handling and so forth, I wouldn't expect to get exactly the same yield or ultimate as another sample. So let's say that if I have 1,000 samples and I'm qualifying the material, then I would have to find, let's say, a bin of strength set between 55 and 57 KSI. Within this bin, anything that has strength within this bin, I'm going to just put it into this bin, and I'm going to call this a class. And between 57 and 59 is another bin. Anything that has strength between 57 and 59, I'll kind of tally those, and I find the number of samples that have strength in that range. Bin is a range. Then I will form a table, and the table is going to look like this. So let's say I'm looking for a 1020 steel, the class frequency 2 samples that have strength centered around 56.5. So this is in between 55 and 57. And then 18 samples that have strength centered around 57.5, and so on. So I just kind of generate that type of table. And then once I generate this table, I put it in a frequency diagram, as you know from your statistics. So on this axis will be the frequency, and on this axis will be the class. So the class has a center point. So the center point will be in here. I have a center point here, center point here, center point, and so on. And then I just tally. I have 2 samples that have the strength in this range, and I have 18 samples that have strength in this range, and so on. And therefore I can build what is known as the frequency diagram that you know of from statistics. And to make things a little bit easier for us, we're going to define this as the probability distribution function, the PDF for short. And symbolically, we're going to call it f of x. So f of x is the PDF, and strictly we can define f of x times the width of this bin, so dx is the width of the bin, as the probability of the strength to lie, which is S ultimate here, to lying Let me just kind of write it here clearly. So this is lying in the interval of x, 2x plus dx. And we're going to call this a random variable. Random variable is S ultimate, which is the same symbolically as x. And that's kind of the definition of the PDFs. So the PDF is the probability of failure, or that the ultimate is in the range of x and x plus dx. So if x is 57 and dx is say 2, then it will be the probability that the strength will be between 57 and 59. That's the meaning of that. But in symbols, we will just say it's f of x dx as the probability distribution function, or the PDF. Now if I continue this discussion, then I would have to describe the PDF in an approximate way, in a continuous fashion. And the most usable description is called the Gaussian distribution function, where f of x is equal to 1 over sigma times the square root of 2 pi times the exponential of -1/2 x minus mu over sigma all squared, and that would be in the exponential. And when f of x is described in this form, then the random variable is x, which is on this side is x. The other parameters are two parameters, mu and sigma. Mu and sigma. Mu is the mean value of the distribution of strength, and sigma is the standard deviation of the strength. Therefore, we can use a shorthand way of writing the PDF, and the shorthand way is n of mu comma sigma, and that shorthand is equivalent to writing this very long expression. So if I look at now the situation, I have the PDF is f of x versus x. It gives me a Gaussian, and it's centered around the mean value, and the mean value is mu right there. So mu is this value here, and when I look at mu is right there. Now if I integrate f of x by integration, I obtain another function that has the capital letter capital F of x, and this function is called the cumulative probability distribution function, or the CDF. So the CDF is the integral of the PDF, and it describes the probability that the strength will be up to a given point. For example, if this f of x is integrated, like I just changed x to y just because the dummy variable is integrated from 0 to x, I will get capital F of x. So if I have a strength at this point here, let's say this is 70 KSI, then the PDF would describe the probability that any random sample that is drawn has a strength up to 70 KSI. So it will be the cumulative distribution function. And then we can now describe the distribution function by either the PDF or the CDF. Usually it is the PDF, and then by the integration we obtain the CDF. So we'll kind of stop the lecture here, and then in the next lecture we will focus on the idea of cold work and how we can enhance material properties.